Let's take a look at basic I/O concepts. I/O is not the same as RAM. So there are three different types of I/O. Write-only I/O, such as what we use for 7-segment displays. So if address 1 is our left 7-segment display, and we've seen this in the lab, if you put a 90 into address 1, it does not read back a 90, it reads back 00. This is an example of write-only memory. You write something, but it doesn't remember what you wrote. However, we're going to see the pattern for an H show up on the left 7-segment display. So the I/O device is updated, but it doesn't send back what we wrote to it to update that device. If we take a look at read-write I/O, whatever you write, you read back. This is kind of like RAM. So in address D, if we put an AA, we read back an AA, and we'll see the binary pattern AA on our green LEDs. Bidirectional I/O is a little different. Instead of just having one address, there are going to be two addresses associated with bidirectional I/O ports. And examples of these are KEYPAD and LCD, which we're looking at in Chapter 4. The two registers are a data direction register and a data register. As we can see here, port A, data direction register, port A, data register. So these are the two registers that you have for port A. And this is where a keypad is hooked up. Now what you have to do first is you have to set up the data direction register to know how stuff in port A data register is going to work. So for instance, a data direction register, pin by pin, you can make them either input or output pins, any kind of combination. For instance, if PTADD here has FF, that means we have all ones, which means they're all output pins. If port A data direction register has 00, then these will be all input pins, but you can make them half and half, F00, F, whatever you want to do. But let's see how that makes things a little different. So if we say PTADD, or port A data direction register is FF, they're all output. And so if in the data register PTAD we put an AA, then the pattern of 3 volts, 0 volts, 3 volts, 0 volts, 3 volts, 0 volts, 3 volts, 0 volts, or the pattern for AA will be out on these pins because output pins remember what you write out, and this is writing that out into port A data register. However, if you say PTADD or port A data direction is F0, then these four are output, and if we try and write out the port A data register having AA, it's going to write out the A, which is this pattern, but it's not going to write out the other A. Now it depends on what the other four lower bits are connected to because these are now input. So if they're connected to input devices, whatever those 4-bit input devices are, that will change this digit. But if you have it connected to nothing, all these lower 4 pins will float high if there's no physical connection. So if you write out AA, it's going to read back AF. So it remembers the A, but it does not remember the other A because whatever is happening on the input happens on these 4 bits here. When you look at keypads and keypad interfacing, there are two different types of keypads. A non-matrix keypad that has one output pin for every key, plus a possible ground. And this is an example of a hex keypad that is non-matrix. So this one and this one look identical in terms of the keys, but if you look at the number of pins coming out, this one has 16 pins, possibly 17 because there's one pin per key, plus a possible ground. A matrix keypad has one output pin for a row, so 0, 1, 2, 3 is one row, 4, 5, 6, 7 is row 2, 8, 9, A, B is row 3, and C, D, E, F is row 4. Column 1 would be 0, 4, 8, C, column 2 would be 1, 5, 9, D, column 3 would be 2, 6, A, E, and column 4 would be 3, 7, B, F. And so what you're going to find is that you have 4 row pins, 4 column pins, possibly a ground pin, so total would be either 8 or 9. So if you go to a surplus store and you look at a bin full of keypads, they may look the same, but the number of pins are going to determine which type that you have. Matrix keypad is the only keypad type that can easily be interfaced to a microcontroller. Now port A is connected to the keypad socket located at the bottom of the keypad. It has the following pins. So port A is what we talked about earlier, and port A is the bidirectional I/O port. PTADD is the data direction register as we saw. Now if you were to buy a matrix keypad, what you have to do is figure out which one of these is row 1, row 2, row 3, row 4, and column 1 to 4 before you can actually interface it. And the way to do that is to hold down, say, the 0 here, and then with an ohm meter check these 2 pins, check these 2 pins, check those 2 pins in pairs until you go through all possible combinations and fill in a chart. So for instance, if I press and hold down the 0 key, that's row 1, column 1, row 1, column 1, If I happen to find that pin 5 and pin 9 make a connection when I'm holding that down, then I put an X on pin 5, an X on pin 9, and I continue filling in the chart. If I hold down pin 1 here, that's row 1, column 2, and so I make a note here, and I might find that pin 4 and pin 9 are connected together. So once this chart is complete, then you can start analyzing and figuring out which is my row 1, my row 2, row 3, row 4, and column 1 through 4 as well. Now if you notice here, row 1 has 0, 1, 2, 3, 0, 1, 2, 3. So these are the pins here that are connected when you hold those down. So this pin 9 is then the row 1 pin. You notice here we have 4, 5, 6, 7. 4, 5, 6, 7. The ones that are common there are these. So this is the row 2. And I think you can see this is row 3 and row 4. Column 1 is 048C. 048C. So this is the column 1. And I think you can figure out this is a column 2, 3, and 4 pins as well. If you were to find that there's all X's down, say on pin 1, that would be a ground pin. But in this case, even though there may be 9 pins, this one is not connected to anything. When you look at a matrix keypad, there's no connection between any row or any column. Now, one of the standard techniques for figuring out if there's been a key pressed and which key was pressed is to do something called keypad scanning. And the concept is what you do is you hold column 1 to ground, then disconnect it, connect column 2 to ground, disconnect it, then connect column 3 to ground, then disconnect it, column 4 to ground, disconnect it, and then repeat this process over and over. If column 1 is connected to ground, what you're going to find all the rows internally here are connected to 3.3 volts through a pull-up resistor. And to do the analysis here, we really have to take a look at this diagram because it's very similar to a switch or push button interface. So in the case here, if none of the buttons in this column are pressed, that's like having an open here. And what that means is that if this circuit is open, then we're going to have 3.3 volts coming out on all of these row 4, row 3, row 2, row 1 if no key was pressed. Now as we continue to connect each one of these in turn to ground, and let's assume at some point we happen to press this 9 key. And if we've checked here, we're going to see that these will all be 3.3, but when we get here we're going to have a different thing happening because 1, 5, and D are not connected, so that means we're going to have 3.3 volts coming out here. Since key 9 is being pressed, that makes a connection between column 2 and row 3, which means this is a connection, which means this is going to be 0 volts coming out. So what you're going to see here for pin 9 being pressed, and it happens to be scanning along here and gets this particular column to ground, you're going to have 3.3, 0, 3.3, and 3.3. And that's how it's going to figure out which key was pressed because it knows only one of these columns goes to ground and only one of these things is ground. So it knows the key that was pressed is at row 3 in column 2, and it's going to generate a binary pattern based on that key being pressed. The concept of key bounce. When you press and release a key, it's going to bounce. So when you press the key, it's going to bounce, so it's not going to be into a steady state area here until about 10 to 20 milliseconds. And when you release it for another 10 to 20 milliseconds, it's going to bounce. And there's a couple ways to get rid of this problem. One is using a capacitor. One is just saying, okay, as soon as I see this thing change state, I just wait 10 or 20 milliseconds and then I take the reading. And then when it's released, I wait 10 or 20 milliseconds again once it starts bouncing to say I'm in this region here. So key bounce is the idea that when you press a key, you're going to get multiple inputs for one particular key press. Now, one of the things we learned about in class was a hex loader, which takes hex key presses and converts them to 4-bit binary. For instance, if I hit a 0, I should get a pattern for a 0. If I hit a 1, I should get a pattern for a 1. And that's basically what we're going to have for most keypad encoders. They're going to generate a 4-bit output based on which key we pressed, based on a standard hex keypad layout. However, what you're going to find is that not all keypads have these characters on the front. But if I happen to have row 1, column 1 pressed, no matter what key happens to be there, I'm going to get a 0. When I press a 1, which is row 1, column 1, I'm going to get 0, whether it's a 0 or whatever character happens to be on the key itself. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. Which 4-bit binary is going to be, when I get a number sign key, it's going to be 1110, which is an E. Now, keypads can have any kind of characters at all on them. They could have Russian Cyrillic alphabet on them. They could have Farsi characters. They could have anything at all on them. And the concept is, if we look at this particular keypad, if I press an A, I'm going to get the pattern for 0. Press B, I'm going to get the pattern for 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So regardless of what characters are on the keys, whatever's in row 1, column 1 will generate a 0. Row 1, column 2 will generate a 2, and so on. Now if you go out and try and get a hex keypad encoder, you're going to find that they're fairly expensive. One way around this is, instead of just having the rows connected to pull-up resistors to 3.3 volts, you actually have the columns connected up to 3.3 volts through pull-up resistors as well. Now to the right, as it says, this is how the one in the lab is connected with extra pull-up resistors. And it says the PTADD, which is port A data direction, is 00. That would make all the pins of port A input pins. And in the case that we have down here where there's no keys being pressed, that means that we have 3.3 volts coming out on our column pins, and we also have 3.3 coming out on our row pins, which means all of these bits all the way across here will all be ones. 3.3, 3.3, 3.3, and so on, as long as no key is pressed in our entire keypad. So if you understand that, then we can continue on and take a look at what happens when we do press a key. How are we going to decide which key was pressed? Now if we take a look at making port A data direction register F0 and then putting port A data register, put a 00, what's going to happen is 00 is going to go out on the row 4, row 3, row 2, row 1 pins, but it's not going to have any effect. There won't be a 0 going out on the other because these are now inputs for the column pins. So what that really means is that if we're putting a 0, that means all of our rows are now connected to ground, which is what we have here. Even with this pull-up resistor, you're going to have 0 volts coming to this point here. What that means is that if there's no key being pressed at all, then all of the column pins are now going to be at 3.3 volts because they're all connected to pull-up resistors here. So that's very important to understand that. Now let's take a look at this case where the port A data direction register is set to 0F, which means it's not going to write out the 0 on the rows, it's going to write out the 0 on the columns, which means now these are all connected to ground. So from here all the way across to here, this is going to be ground. If there's no keys at all pressed on here, then what we're going to expect to find on all the rows is 3.3, 3.3, 3.3, and 3.3. Now let's take a look at the case where we actually do push a key, and let's make that key be 6 on our keypad that we've got here. If we use PTADD as F0 and put 00 out, it's going to write zeros again to the row side here, which means that every point out to here is going to be ground. Now if we take a look here, that means that if we don't press any keys, all the column pins here are going to be 3.3 volts. But notice we got C4 here, C3, C2, C1. C4 is going to be 3.3. This is going to be ground because we were actually connecting that to ground. And then C2 and C1 are also going to be 3.3. So C4, C3, C2, C1 is going to be 1, 0, 1, 1. And if we store that away somewhere, we'll know which one of these columns, in this case column 3, key was pressed in. Now let's take a look at changing port A data direction register to 0F. That means we're writing zeros out to the columns, which means every column is going to be connected to ground, which means every column pin is going to be ground to this point here. Now what it's doing now is checking the row pins. Now I think you'll see that if all these here are ground, R4 will be 3.3, 3.3, 0, and 3.3, which is what we have here, 1, 1, 0, 1. Now if we take and combine the results we had previously with this, we have 1, 1, 0, 1, which means row 2, and 1, 0, 1, 1, which means column 3. Wherever the zeros are, that's the row and column of the key that was pressed. So row 2, column 3 is a 6, and that's the way we figure it out. Now let's take a look at the LCD that we have in our lab. Pins 1, 2, and 3, the left 3 pins, are actually for intensity control. One of these connected to VCC, one to ground, and one to a wiper on a pot. And you can use the pot to actually adjust the intensity on the screen. But these next 3 pins are called control pins, RS for register select, RW for read write, and E for enable. And then the next 8 pins are data bus pins, and notice it's D7 through D0 here. Before you start using the LCD, you have to send it a couple of instructions. And later, once those instructions are processed, then we want to send it ASCII characters or alternate character, and then use the control bus to actually tell it that it's either a character or it's an instruction. Let's take a look at RS. It determines whether the information on the LCD data bus is LCD instruction or character data, being alternate or ASCII. And so that's this pin here. So as it says here, if it's a 1, it means that what's on the data bus over here is an ASCII or alternate character. If it's a 0, it means it's a LCD instruction. Now the read-write line here, which is this guy, determines the direction of flow. Is it information going from the microcontroller to the LCD, or from the LCD back to the microcontroller? Most things that you want to connect up are going to be from the microcontroller to here, which means the read-write line will be low because we're sending stuff, writing stuff from the CPU to the LCD. Now the last control pin that we've got here is enable. And what that is nothing's going to happen here regardless of how you have these two until you set this high, and then on the falling edge of E, whatever here is going to be processed based on how you set up the RS line. So as we said, the first instruction we have to send it is a 38, and we have to tell it that it is an instruction. So first thing we have to do is put the 38 on the data bus. Now notice our data bus is backwards, so it's 0011, that's 30, 1000, so that's our 38 that goes on here. The second thing we have to do is tell it that it is an instruction. So that means the RS is 0, saying that this is an instruction that you're going to be dealing with. The read-write line is going to be set to 0, saying that we're storing that value 38 from the CPU to the LCD. And then what we have to do is set the enable, which is normally low, set it high, and then on the falling edge, when we set it back to ground, then this will be processed as an instruction. Now altogether there are two instructions that have to be processed, a 38 to actually tell it that it's a multi-line display, and a 0C to actually turn the display on. These are the minimum instructions you can use to get the LCD initialized. Once you do that, now you can send it alternate characters or you can send it ASCII characters. Now on the PCs you might have seen that F8 is a degree symbol, but on the LCD a DF is a degree symbol. So let's just say we want to throw a degree symbol up on the display. So what we have to do is we have to put the value DF 11011111 on our data bus. But this time, because it is not an instruction, it is a character alternate or ASCII, we make RS1. Again, we're still storing this DF from the CPU, the accumulator, to the LCD. So this is still going to be 0, saying we're storing. And again, what we have to do is set the enable high, and then on the falling edge of this, it's going to actually then display the degree symbol on the LCD. A number of Arduino-like functions that the LCD uses. LCD set cursor, and if you remember that this is the row, this is the column, and we'll take a look at how that looks shortly. We have LCD print to print messages. We have LCD write to actually write the actual value 4A to the LCD. If we say LCD write character and we give it a DF, that's going to put a degree symbol up on there, and then if we say LCD write character C, it's going to say C, so it's going to say degree C. Now there's a function called scalar, which is really quite neat. And what scalar does is scales 8-bit A to D values from 0 to FF into a meaningful range. What that means is that if we take a look at this line here, Bob equals scalar, and it's going to do analog read integer here 0, which means it's taking the input from TP7, and let's just assume that that value is 800. What it's going to do is shift that 800 4 times to the right to make this 80. So what it's going to do is it's going to take the 80 and it's going to say, well, what is that number? 80 is half the range of whatever, and what this number is here is this is what's going to be displayed. So right now half of 25,000 is 1,250, 12500. And what this is saying is we want a 4-digit display, 1, 2, 3, 4, 4 digits. This is saying where the decimal point is. Now if it was 0, the 0 would be here at 0.125, but since we put a 1, it's going to be 1.250. If we made this a 2, it would be 12.50, and so on. And the last two digits here specify where on the LCD display this number is going to be displayed. So 2 and 6, remember this is row 0, row 1, row 2, row 3. So it's going to start here at row 2, column 6, and it's going to write down 1.250 based on half of this value and putting the 4 digits and saying the decimal point is going to be not here, but here 1.250, and that we're going to have this displayed at this particular coordinates on the LCD.